Bhaskar, we can wait for another 1 minute and start. There are multiple people on the streams also, so welcome everybody. And we can just wait for a minute and then we can start. We may find some people having a little more struggle to join this time because they have to create an account, right? So that's the one thing.
I think I got a couple of messages from people. There were some issues in.
Yeah, so you can navigate through this page. You can navigate to help and FAQ, and then if they go to help and FAQ page on the multi-cloud side, I think that would be enough for them to, if they have any issues. You can show that also through Chrome if you want before you start. Yeah, so there are a lot of people waiting on the stream also. So I think we have a good quorum to start.
Yeah, let me know when we should start.
We can start in another 30 seconds. That's max.
Okay.
Okay, so start. Yeah.
Cool. All right. So welcome everyone to our today's session at Multi-Cloud for You. Today we'll be talking about an optimization-based AI model, which basically models one of the life and death scenarios in a typical hospital's ICU setting. So before we start, I'll quickly run through the introductions and then what exactly we do at Multi-Cloud for You, and then we'll begin with the agenda and the contents for today. So introduction about myself. I am a product evangelist and a researcher. I have over a decade of direct service to IT industry, and one of the things that I am doing is that I am a PhD research scholar, and I have some good experience in the field of mathematical optimization and nature inspired computing algorithms, which is one of the topics of my objectives of my PhD research works in the mathematical finance area. And my LinkedIn profile and the bit.ly link is given here. You can join or contact me at LinkedIn. Moving on about Anjani. So Anjani is the founder of Multi-Cloud for You. He has been a leader, inventor, mentor, and enabler, and he has enabled and mentored people at different levels. Right from school kids to different corporate giants, and provided some strategic insights and consulting to various organizations at different responsibilities. Anjani has over 17 years of direct service experience in the IT, and he has an added 5 years experience as an entrepreneur. He has been driving ventures from scratch, builds them, and then moves out to the another ventures. Anjani can be contacted at the following LinkedIn profile, and here's the bit.ly link as well. Now, moving on to Multi-Cloud for You. So what we do at Multi-Cloud for You. So basically, we started as a community of cloud researchers and engineers who came up together, and basically we are a group of engineers, scientists, and researchers who solve challenges faced by the different businesses in managing cloud asset and frugal productionization of cloud technologies across various cloud technology stacks. And we also share our experience and the insights that we gained from all the implementations we've done in past and present, and share that with our community members, and for the benefit of everyone in a very unbiased perspective, and mostly it revolves around all the aspects of the technology stack, whether it is consulting, whether it is training, or practicing, or live production problems, or troubleshooting, and so on and so forth. We also provide, cloud value proposition based on short term as well as long perspectives. Our insights are mainly, on the cloud, where the customers demand our insights are, it's mostly on the, speed, OPEX, CAPEX, security, and vendor lock-in aspects. Although, there are various other multitude of, areas where we are also providing our strategic insights to various firms. Our cloud AI research lab collaborates with top researchers across industry and academia, and we kind of build open source solutions for the industry. And then we normally share in sessions like we have today. We share the learnings and the real world settings with our community. So we can be, reached at multicloudforyou.com, and you can also join our WhatsApp and the YouTube channels by these QR codes. Okay. So let's start with today's agenda and the contents. So what we plan to do today is that we'll talk about the life and death scenarios and what are the real world settings where we have some problems which can be solved effectively by the usage of some NP hard problem solving algorithms. And we'll take the case of one of the algorithm and we'll discuss the philosophy behind it, why we chose that particular algorithm, and why do we really prefer nature-based algorithms or methods in such situations over other deep learning models and various other AI implementations. And we'll talk about the basics of particle swarm optimization, which is one of the nature-inspired methods we have used for solving real-world problem of ICU setting in the hospital. And then we'll try to discuss the methodology and the results and that we achieved, and finally what we have concluded. We'll also talk about, Anjani will in detail talk about the deployment and the productionization aspects. Okay, so let's start with what are the real world life and death scenarios. So there are often scenarios where we leave the life and death decision of a human in hands of a AI program or the robots. So this is already happening in a lot of cases. And so one of the questions you might be wondering is that how comfortable we are leaving life and death scenario decisions up to robots or the AI programs. So right from autonomous cars to drones deciding what targets to hit to robotic doctors, I think we are already at a point where machines are playing effective roles. In some cases, they are taking the decisions, while in other cases, they are providing decision-making intelligence to the human beings or the decision makers. So I think there have been significant breakthroughs in this field. And right now, one of the evolving fields is obviously medical AI. And with the current scenario and the situation that we are facing for the COVID-19. So I think medical devices and clinical decision making, they are really getting popular. The usage of AI in scenarios like end of life care, ventilators. There are ICU equipments which are churning a huge amount of data, medical sensors, critical disease diagnosis. There are cases where we predict fatality likelihood of the indicators, for the patients who are already in, you can say, the ICU or HDU setting. Apart from that, I think one of the other areas is clinical decision making, where you can say they are mission critical or life or death scenarios where we provide intensive clinical data analysis. AI programs are effectively taking decisions or giving prescriptions as robo prescribers to the physicians, and the front desk service staff, and ventilator associated disease detection. They are also evolving towards hyper personalization of the treatment plans which are personalized for specific patients. Apart from that, there are obviously uses of these kind of mission critical applications where you have robotic control systems or railway or aircraft control systems, combat or rescue drones, autonomous cars. I think there are a hell lot of use cases where you can apply these kind of methods, which we'll be talking about in the next few slides. So, life and death scenarios, in short, are mission critical scenarios on which a human life depends, typically in a ICU setting within a hospital. So, when you go to hospital, you would one of the problems that patients often face is the problem of sepsis. So today we are going to discuss about one of the scenarios where we discuss the problem of sepsis and how do we resolve that within the ICU. So sepsis is one of the most frequent cases of admissions in the ICUs and also one of the most common causes of death. So treatment for sepsis usually begins with antibiotics and intravenous fluids and a couple of liters at a time. Now, if a patient, does not respond, they may go into a septic shock, where the blood pressure would drop dangerously low and the organs might fail. So this is a very common scenario which happens in a lot of, ICU settings. Even, patients who are not in the ICU, they may be in the HDU setting. There also, it is mostly up to the doctor to provide, to basically stop the fluids and provide some vasopressor, medications and raise the blood pressure. So this is where I think it gets tricky, because administrating, any fluids for a very long time, so that may not be very useful. So what happens generally is that, patients need some vasopressor treatment early. On the other hand, if the doctors give a too early treatment, so that is equally negative for the ICU patient's health. So I think net it becomes a judgment call for the doctor, where you can imagine the doctor taking a biased or an unbiased or an incorrect judgment, uh, just because of the lack of enough data. Although the data is present, but the lack of insight from the data. So I think this is where it really gets tricky, and there is the role of AI, where it can solve the problem of, for this particular case, how do we predict when the sepsis is going to happen and when the doctors can take an effective action. So what we have done is that we have taken a real world case, which is the data set for this case is already given on the UCI data. And I think UCI is a dataset repository which most of the data scientists would already be aware. It is a repository where the popular datasets of machine learning are already available, like Bikeshare, Iris, and so on and so forth. So what we have taken is the full dataset, which includes around 34 variables. The variables are obviously sepsis, which is the response variable, which we have to predict. Then we have age, we have fasting blood sugar, INR, platelet count, eosinophils, basically all the factors, or you can say the independent variables which may cause sepsis, and basis of that we would predict sepsis for a particular date time stamp and when it would happen. So now the question is, what are the potential solutions that we would be looking for in a typical machine learning world? So there are options like statistical models, which is one of the good options, was used early on, but not being used anymore in most of the hospital settings, because one of the drawbacks is that we need to transform all the linear data to the non-linear data of the real world to a linear setting, which effectively causes some data loss during the transformation, and obviously some associated noise. So we do not really talk about statistical models anymore in the real world settings. There are some supervised learning models which do provide some effective clinical diagnosis, but they cannot be used for all the scenarios. Yet they are helpful when they get hybridized with other models. Then we have another option of using deep learning models, where we can apply different strategies of deep learning to give real time to give not real time but near real time forecasts. But one of the problems, as you would already know, with all the deep learning models is that take a lot of time to get executed. So this is typically not very helpful in an ICU setting where we are already racing against time. So the other option which people are looking at are optimization methods, which I think to my mind has proved to be one of the very effective methodologies to cater and solve problems of this nature. So optimization models also are not as fast as supervised learning algorithms, but certainly much faster than the other deep learning models, and they provide nearly, if implemented correctly, they nearly provide the same capabilities that the deep learning models would provide. So we'll talk about, in this session, we'll talk about the use case and how we have solved it using an optimization method. But before I talk about optimization methods, I just need to give you a very high level overview that how and why we should, and what should be the philosophy when we choose an algorithm to solve a particular problem, and especially in the context of AI and machine learning, where we have problems of different areas and different complexities and different um, constraints, where we have data and all. So how do we basically choose a particular algorithm? So I think as my thinking has grown, what I have realized over a period of time is that there are often two relevant questions, and therefore there are two choices when we choose an algorithm. So what are those? So for a given type of problem, what is the best algorithm to use? That should be probably the first question that we should ask before we propose a solution. Next, I think for a given algorithm, what kind of problems can it solve? So obviously, it's not easy to answer both these questions, but I think if you think again, probably the first question is little harder to answer than the second one, because I think in the second one we have a lot of research literature and the demonstrations and examples already available. But the first question is nearly difficult to answer. When we have to make a judicious choice. So I think the answer probably lies that in the free lunch and no free lunch theorem, that there is no particular algorithm which is best fit for all the cases. So basically what it says is that any algorithm cannot be generalized to be used for all the different kind of data sets. So I think now how do we decide then? So one of the things that we should consider in those cases is that what are our computational costs, what is the software availability, and how much time you have to you have at your hand to produce the solution. And I think that is one of the most important factors to decide what algorithms to use. And on the other hand, for a given algorithm, the type of problem that it can solve, I think that can be explored using various kind of comparing and ranking techniques. And I think we can already research on the amount of literature that are talking about the advantages and disadvantages of a problem. So it's mostly boils down to your overall experience in tackling these kind of problems. So one problem that solves quite generically is swarm intelligence approach. So this is a nature inspired approach, where you would see that you know, so this example, as it says, defects. So here, if you consider single ant, it may not be, so it would never be, so powerful that it would form a bridge between two, different sections of a building. But here, if you would see that, as a group, what they are doing together, I think this is something which is like beyond imagination. Fantastic. And if you see the ants at the lower section, you know, they are kind of doing their job, and the top section, they are kind of, doing their job by just remaining static and providing the guidance to the ants which are moving in the direction on the top layer, right? And they are the carrier ants which are actually going towards the other end to form a bridge. So I think this collective group displays a lot of intelligence, and this is like a phenomenal intelligence. So the philosophy behind all these algorithms, biologically or the nature-inspired algorithms, is that, whenever you want to solve a problem, you can probably make a swarm of all the, species, particular kind of species, whether it is fishes, whether it is ants, or whether it is a flock of birds which, go together and, fly together in search of food and cross the entire ocean, right? It would be very hard if a single bird is going to cross the ocean in search of a food. So I think this is where, the philosophy, and you see from these images, these are quite phenomenal real world images which can be seen on the internet, which have happened in the real world, which depict that there is some kind of intelligence in the nature. So it's basically, the philosophy is that nature has a mind of its own. It is self-adjusting, it is self-organizing, and based on these two attributes, it can, solve problems which we called in our machine learning world as NP hard problems. So, what I want to talk about next is, what is the this swarm intelligence? So, I think one of the fastest growing subfields in the field of, AI and computational intelligence is soft computing and evolutionary computing, as we call it. And this is, this field includes different optimization algorithms that are suitable for solving problems which are NP hard problems. NP hard problem is something where you cannot get an exact solution, because the exact methods would be inefficient, or they would be underfit, or they would be overfit methods. In these cases, what we generally do is we use some stochastic operators, or we call them as gradient free operators, which is like, let the groups form together and self organize and reorganize based on the reactions. So if you have to solve a financial time series or predict the price of a financial security, and if you apply a nature-based method there, so as per the volatility and the noise of the financial time series, these methods are capable to basically model themselves, readjust themselves, and respond and provide near exact solutions. So they will never provide an exact solution, but a near exact solution which will help them, the decision makers, to take an effective decision. So I think this is one of the insights which is very helpful in solving real world problems. So I'll take another example where we have a piece of a group of honeybees. So they would cross from so let's say the hive is in the center of the city. So a honey, and there is a countryside which is like 5 or 6 kilometers away from the city. So in these cases, a single honeybee, a individual honeybee, or a swarm of honeybee, they would typically go and get the honey, uh, just having a very small brain in comparison to the brain of a human being, such a tiny brain, but they would remember the exact path that they traversed, and then they have the capability to just retrack that path without getting lost or without colliding between the group. So I think this is something phenomenal which should be used, That was the principal philosophy behind all the nature-based algorithms. So typically, the scientists, nature-inspired scientists, they have derived 5 principles on which we have created all the algorithms of the nature-based intelligence so far. So that is proximity. Let's say there is a flock of birds. What is the proximity of each bird from the neighbor? So from its current 2 neighbors or adjacent 3 neighbors, and so on and so forth. And what is the quality of the swarm? So basically, the quality of the swarm is basically that the swarm would any particle or any bird or any fish in the swarm would never collide with itself. So imagine we are driving in a uh, non-COVID setting in a Delhi road or a typical city where we have a huge traffic, and there are accidents. But in the world of nature, typically in species like ants and species like honeybees and species like birds and fishes, there are no collisions or rarest of the rare collisions. So the quality of the swarm is very good, and then its response is very diverse. So let's say a single bird, if it finds some food particle, then the entire swarm would follow that single bird, and the personal best would become the swarm's global best. So and then obviously there is stability and the adaptability. So together these principles create a swarm intelligence approach. Now, how do we solve the problem? So before we solve the problem, I want to showcase you the code and of course the real world database so that you can understand more. So what we are doing here is that we have taken the sepsis dataset, which has around 34 variables starting from sepsis, age, HTN, fasting blood sugar, so on and so forth, right? So what we are doing here is that since we know that there are around 36 dimensions, right, 36 columns. So first thing that we need to do is to reduce these dimensions and figure out what are the most important ones. And what we generally what have we done is that we've taken all the features, then we have generated a subset of the feature set, and then we have evaluated that subset feature set where we see that okay, these are the most important variables which are driving the indicator of sepsis. So anything which is more responsible will be there, otherwise the less responsible variables would be eliminated. So first we try to run a random forest classifier where we figured out what are the most important features, and as you would see that it gives us the most important features. Then what we have tried to do is run a grid search. So basically we try to run a support vector regression on these cases where we optimize the support vector regression by a grid search algorithm. So grid search is something which is kind of a brute forcing mechanism, but not really a brute force. So it will typically search the hyperparameters which within a given range. So for C and gamma, which are given here 0.001 to 10, I can give a range, and within this range it will try to figure out what are the best parameters. So once we choose the best parameters, then it will apply those best parameters as the input set, and then finally we get an accuracy. So here I think since we have already optimized the parameter here, so as you see the root mean square error is 0.6, which is kind of a very low error, and the mean square error is 0.028, r square is 0.93, which is like huge. But we still do not know whether this is the best method, or typically that Python library has already given this a grid search method, and now we have to test whether our well, we will expose this as a service. We are trying to we'll expose this service as an optimization service. This is not just one method. There are like hundreds of other methods that we are trying to build up, and we are currently in the process of developing a optimization library where we'll expose all the methods for the developers. And obviously it's a free community, so we'll keep adding those algorithms to our data bank. So I think more than code, what we need to understand first is the concepts of the nature-based algorithms and the methodology, which is more important than the code, because then the pseudocode is available all across on the internet, which can be easily gained. So I think we'll definitely provide the examples and the ready-made help. So what we do here is typically talking about the particle swarm optimization. We extract the data, pre-process it, then we make it ready for the consumption of the algorithm by doing the various transformation and eliminating any null values, or scaling or normalization or standardization. Once we have done the data pre-processing and our feature engineering, then we divide our data set into test and train data set, and then we take the trained data set and then provide a range of parameters for the support vector regression model, which are just the input sets which go in a typical input for the support vector regression. And now within this we initialize the particles. So I'll before I talk about the methodology, I'll come back to this methodology, but I want to show you how the particles are initially distributed and how they converge together. So typically this is the setting where you see that for the iteration 1, I have given some parameters where the weight parameter decreases from 0.9 to 0.4. C1 and C2, which are the acceleration and the social cognitive components, which actually keep changing or remain static as provided, and then we converge all these. So initially all these are randomly distributed within the search space, and when gradually we run this algorithm, so these start converging as we increase the iterations. So this is kind of a swarm where it is a self-organizing swarm, and it is actually moving towards a local optimum, or you can say a global optimum, based on whatever is the requirement stated in our algorithm. And once it reaches a convergence, we'll wait for, yeah. So as I said, that these are inexact solutions which do not provide exact solutions, but near exact solutions which are good enough for decision making. So you would see that not all the particles have converged here. These are as we increase the iterations, maybe these would converge or maybe these would not converge, but certainly all the particles which were initially distributed at a very random search interval space, they have finally converged together. So this is kind of an self-organizing swarm which is realizing the problem and then organizing itself as per the needs of the the data, and based on that it's learning from the data, it self converges. Now there are loopholes and there are improvements which can be done here. There are problems like getting trapped into a local optima. For example, here so this is a typical setting where I would say that the swarm gets trapped in a local optima. In one case, we balance the exploration, which is kind of a explorative tendency of the swarm, and the exploitation, which is kind of the intensification tendency of the swarm. So in the center example, we balance them. The first and the third examples are the rare examples where the swarm either converges too fast or the swarm converges too slow. So let's see how it happens. So as you see here, the iterations are increasing, the weights are changing in the central case, the inertia weight is changing, and it is kind of moving towards a global convergence. And finally, by the end of iteration 50, you would see the first swarm has converged very quickly, most likely it would have hit a local optima instead of a global optima. But in the center case, it is a well balanced form, which is kind of having a equilibrium between the explorative and the exploitative tendencies. And the third is kind of an exploratory swarm. So depending on the type of problem, you can use this setting, which is called particle swarm optimization, in a real world setting, and solve different types of problems. So as in what I mentioned was, we could solve problems of forecasting. We could solve problems where it requires local minima convergence. We call mostly these problems as convex optimization problems. So coming back to our methodology, here we first initialize all the particles in the random way, as you saw in that example. Then we put some different strategies. As I mentioned, there are 3 strategies. So one of them is linearly decreasing inertia weight. Similarly, we have the constriction coefficient, and I'll not go into the details of the training strategy. It was just that since this is the first session, so I just wanted to cover that you can employ different strategies and calculate a particular fitness value, and based on the fitness value, then those particles or the entire swarm updates its own fitness value. So let's say the fitness value of one particular bird among all the birds of the entire flock of birds is more than the entire flock. So that personal best of the bird becomes the global best, and the velocities and the positions of the entire swarm are updated with the personal best of the that bird. So basically here, as we say it, G best becomes the P best, and we do this, keep doing this till the best condition or the exit condition is reached. And finally, once the model is trained, we feed the cost and gamma parameters. So here, as you would see that we were typically trying to deduce the cost and gamma parameters by running this algorithm, right? And once we get the cost and gamma parameters, or for that matter any weights, or any algorithm would have its own inputs, we can just optimize the inputs of any algorithm here, right? For this case, we are using support vector regression. So once we optimize this, then we apply the same thing on the test data, and then try to compare the accuracy. So as I mentioned, in the code that we were seeing, that grid search is giving a very beautiful result, which is like 0.16, MSE is 0.028, which is fantastic. Similarly, we can apply other standard methods given by the Python library, which are random sets, random search methods. So these are also giving very nice results and efficient results. So we have kind of done a comparison of the results that we get from the different methods. So see over here, we optimize the first one with the grid search. So this is about the real world results which we got after running around 50 iterations each for each of the algorithm. So a root mean square error of 0.29 and R square of 0.90 was obtained after running all these 50 times, each of them 50 iterations. Now these are the standard libraries of the Python and R libraries, standard functions of the Python and R libraries. And this is our algorithm, where we have employed 3 different strategies, and you would see that it just beats out the beats out these standard libraries flat, where we see a drastic improvement in the root mean square error. So this error should be as near to 0 as possible. 0.15, when you see the R square, this also increases by almost 4%, right? The k-fold accuracy mean also increases. So I think typically this thing has been proved that nature-based algorithms like PSO or ant colony algorithms and so on and so forth, these algorithms are very helpful in solving our real-world use cases, whether it is the area of retail or finance or healthcare, or any particular sector. You can also see that this is the accuracy of our trained and the test results. So most of them, as I said, it's a near exact solutions. There are some outliers, but most of them, as you would see, are modeled correctly. So I think the residual is performance is very good here. And then we will also finally talk about the modeling approach. But before getting into the details of the modeling approach, because I think that's something which we can share with you offline as well, and you can watch this video also, which is kind of self-explanatory. I would like Anjani to talk about the deployment of this model, and then how do we convert this this model in a real-time production setting and expose this as a service, and then finally consume this. Anjani, I would request your presence here.
Yeah. So you, hello everybody. So you can see that any model that you design, right? So either you design it through the designer or the notebook, you have to train it, and then when you're training it, as I said, like you have to use GPU processor, VM. You can set up, you can choose the best VM or the GPU processor as per your training need. You can do it on Google Colab or any other cloud platform, maybe Alibaba Cloud, it's Azure, GCP, anywhere. And then you generate the weight file, or there are consecutive files that most of this training model generate, but ideally we are calling it here as a weight file. Bhaskar, can you just, okay. So now when you talk about DevOps, so you can automate it in two ways. So but the generation of the weight file can be automated through weight file gen and deploy, right? And then you can add it through, add your GPU or a low cost VM through Kubernetes and Swarm, Kubernetes Swarm, and the and set up VM, and then you can either containerize it, or even through Anthos in Google, you can add the VMs directly. It depends upon you. And then you can use one of the studio or one of the inbuilt tool, like Alibaba has Alibaba PAI. Similarly, Azure has its own machine learning studio, and all of most of this major platform, AWS is own. Extend it to any language as you like, and once it's there, you may be using some more environment, Keras, TensorFlow, based on your need, Music 21 and Python. Once it's all done, you can deploy it. Yeah, so Bhaskar.
Yeah. Thanks, Anthony. So I'll talk a little about the actual implementation that we have done. So, guys, I think there's some echoing. Yeah, looks like it is fine now. So, as I said, to implement particle swarm optimization, first we need to initialize all the parameters. We need to provide how many neighbors. Just going back to those 5 principles of swarm intelligence, how we model. So what we generally do here is, let me open that slide. Yeah, so we are seeing proximity, quality, diverse response, stability, and adaptability. Now, all these principles we need to model mathematically. What we are doing here is that we are setting the count of neighbors. So, what is the count of neighbors for each of the bird, right? We are setting up some acceleration and the cognitive component. So, cognitive is what is the basically and so this is a cognitive, you can say it's a kind of a coefficient for a particular individual particle or a bird, and this is coefficient for the entire set of the flock, right? And based on these two, we try to we have also tried to avoid so as I mentioned that we have tried to implement some premature convergence where you would hit a local optima instead of getting a global optima. So we have kind of tried to create a phi number, as we call it, by combining a constriction factor, and based on this constriction factor, basically what happens is that we and we have also initialized the weights. which is like we moved from 0.9 to 0.5 as you saw in that image, right? And we have coded a fitness function where you would have a fitness function. Typically in our case we have hey guys, am I audible to everyone, or there is some noise? I am not audible at all.
You are audible. You are audible, Master.
Okay, okay, cool. So what we have tried to do here is that we created a swarm, initialized the swarm, and then we applied a loop where we move through the iterations, and within the iterations we tried to get the global best and the local best, and based on the global best and local best we tried to update the particles position and the velocity, and then therefore we got the entire group's global best across the different iterations. Okay, thank you everyone. Yeah, so I just wanted to show the output how we have arrived at this. So initially we started with these random variables which were distributed across the search space, and then finally the swarm started converging, and as you see that we move across the iterations, the global best, the cost and gamma functions that we have reduced, the training error rate, it keeps reducing with every iteration as the swarm converges. So you would see here the swarm is slowly converging, and ultimately it would converge to a single dot, and that depends on how many iterations you run, what kind of constraints you have put. So you can put any real world constraints and finally arrive at a place where your swarm has totally converged, and then you can do a comparison of your model with the remaining models that we have already done here. So I think net this is what we wanted to demonstrate. The code, as you said, will be exposed as an optimization service, and what we'll do here is for the benefit of everyone, in future we'll deploy the model, and as engineer said that we'll expose the service. So in that service what we'll do is that we'll just expose that service which takes the input and gives you the output. So this will be this entire concept will be an abstraction for you, and you just need to understand what are your input parameters and what is your desired output, and what is the algorithm that you would use to optimize. In this case we have optimized a support vector regression. You can optimize an artificial neural network, you can optimize any specific algorithm which you would take in machine learning. I think almost nearly all the algorithms can be optimized by this approach, and hence we call this optimization approach as particle swarm optimization. So yeah guys, I think this is all we had to talk. The one thing that I wanted to end with was that this is an evolving field of soft computing, as I said, and it has a lot of research publications across the globe happening, and as expected US and China are leading the pack of the AI research, specifically the swarm intelligence and optimization research. But as you see, India is not too far behind. The bulk of the research is focused on within the European countries, and significantly Italy and Iran are two specific players, countries where I think if you want to learn more, you can join their developer communities. China obviously and US for that matter has put everything. Most of them is on GitHub. For China, they have their own version of GitHub which is called code.net. So you can join those communities and get more hands-on into this optimization field. This is something which has not yielded as yet too much. Very few people in the world of machine learning are aware of these aspects of computing. So I think this is one good area to get early on, and get an early adapter advantage. Typically, this is what we do at multi-cloud for you, or talk about these technologies which are typically, years ahead, or, which are forthcoming technologies, and we talk about them, how to specialize and get ready before everyone gets ready. So that's the intent, and you can ask your queries and reach us at IR Anjani at our profiles, or you can also log in into our WhatsApp community groups, also in our register at multicloudforyou.com site. Yeah, that's it. So with this, I would open the forum for any questions. Well, Chinese equivalent of GitHub is, I think it is code.net. Let me just try to open if I exactly remember the URL, but I think that's a very good, site which I have recently of late learned. Uh, I'll probably share. I do not remember if it is code.net or some Chinese name was added to that, but I'll definitely share that with the group. But yeah, I think it can be Googled, Atul. This is something which has really helped me in understanding swarm intelligence more. And I think Chinese developers specifically, I would talk about few universities like one of the universities is Nanyang Technological University in Singapore, which are doing a very good research work. And then there's Beijing University and university in Wuhan, who are really taking this field to the next level, and they are applying this in the manufacturing industry, in the retail and whatnot. Okay, yeah, I think see other useful nature way. That's a very good question. See, so as I said that soft computing, or you would say that nature-based inspiring, nature-based algorithms is all about learning from different species, and then uh, basically solving, understanding those species, and then categorizing and making mathematical models. So typically, you would see a lot of work done on ant colony optimizer. I would recommend the first version is ant colony, as we call it as ACO method. Then there is particle swarm optimization. There are genetic algorithms which people might have heard already. Then there are firefly algorithms, honeybee algorithms. There are, I think there is a huge collection of almost like 80 to 90 algorithms. And as you asked before, I think what we'll try to do is we are kind of building a library of all these algorithms, and most of the libraries will be kind of self-explanatory, and exposed as service, where you would know what inputs you need to supply, what problem it solves, in what kind of settings and data you can solve those problems, and what output it gives, and how to consume that output. So I think, yeah, that's something which we plan in future, and we are already working upon.
There's one question from the stream is like Satish is
Okay.
asking that do we share this recording? So yeah, so we share this recording already. Like once the session is over, once the recording is done, we share it on our different pages, Facebook and Twitter. And also the link is mostly known. So Bhaskar, if you can just direct to the evangelism link, evangelism.
Yeah, sure.
And here, if you scroll down, you will see all the past sessions. You just have to go there, hit the link, and you will be able to watch any of the session that you need. But you may have to create
Yeah,
again account
you
sign
just
in,
need to
and that
register.
Yeah. So, and if you find any issue, you can go to help and FAQ page or open the window in incognito. It's also at the top. So you see there is in the black screen at the top, our stream and sessions are free. Sign up to watch. You simply click that out. It will be on every page wherever you fall in. You will go there, and then there is a demonstration at the top. If you run that video, it will show you how to do it. And then also there is a help and FAQ page. Scroll down, Bhaskar, if you can scroll down, so you will see, are this webinar free? All your questions, if you need to connect to us, if you need to connect to our Telegram channel, to directly talk and connect to us, everything is there. There's a direct phone number in US, in Singapore, in India. A lot of things. You just use this help and
Yeah,
FAQ.
guys, I think better would be that you just land on this site, and then I think that then on the journey is kind of self-explanatory. And we also have a Facebook streaming channel where a lot of people are already watching this video on the Facebook channel. Typically, for each session, we have like more than 1,000 users, who are joining and being part of the session. After the sessions, those who missed the recording can also view this session on our website, our YouTube channel, our Facebook channel, and various other channels.
Twitch, Periscope is also there.
Yeah.
We stream there also, and there is a podcast link also. Bhaskar, you can go to the podcast in the evangelism radio, right? So
Yeah.
in the radio is like if you're walking, obviously in the lockdown days, everyone is at home, so
Be
not
watching this
much
video on
travel
the
time.
Facebook
So
channel.
it's all it is
Yeah.
streaming. So you just put in your pocket, walk anywhere, and you can listen it.
I think you can
Thank you,
add this
everyone.
link to your favorites and just lock your phone and put it in your pocket and keep listening to all the technical stuff, all the discussions happening here.
Yeah.
Right. Guys, thank you everyone for your time, and it was good talking to all of you.
Yeah. Thank you, everybody.
Yeah. Thanks everyone. Bye.